Hi, I'm Chen Shun from National Tsinghua University. This work is co-worked with Professor Ming Sun and Professor Huan Zhongchen. I'm excited to be here to introduce our work about the Voxel grid optimization for phase random field reconstruction. The input to our method is a set of images, typically 20 to 200 images that capture the scene. The camera parameters are assumed to be known or be correctly solved by SFN algorithm. Our goal is to render images from novel viewpoints. NERF emerged as an appealing method for this text for its quality and flexibility. In a nutshell, NERF uses an MLP network to take a position and a view direction as input and predicts the corresponding color and density. The color and density prediction for the sample points on an array can then be accumulated into a pixel color using Voronoi equation. Finally, the MLP network is optimized by reproducing the training views. NERF achieves excellent quality and flexibility, but it is very slow due to the processing time of MLP network, which typically requires many hours to train for a single scene. To speed up, one method is to replace the MLP network with Voxel grid, which can reduce computation from a few 100,000 flux per query to constant time computation per query. Previous work have shown good speedup by replacing the MLP network in inference time, meanwhile maintain good rendering quality. However, they are limited to speed up only in inference time, and the training still relies on the MLP network. In this work, we investigate how to train Voxel grid directly from scratch. There are two keys to make it work, missing one of which results in failure. The first key is what we call post-activation. To produce sharp surface, we find that it is critical to activate the volume density into alpha value after trilinear interpolation. As a comparison, pre-activation activate density to alpha first. We show toy examples by fitting a single 2D grid cell to a linear surface. In this toy text, post-activation can produce a very sharp surface, while pre-activation can only produce blurry surface. We prove in our paper that post-activation can be arbitrarily close to a surface beyond linear. Our experiment also showed that they could result in up to 2.8 PSR difference for non-view synthesis. The second key is the low density initialization, which is to initialize the density grid so that the initial alpha values are close to zero everywhere in the space. And we use a hyperparameter alpha init to control it. We show that the alpha init should be small enough to achieve good results and to avoid float artifact. Our scene representation are simple. To model the volume density, we only use a Voxel grid with the introduced post-activation and low density initialization. To model the view-dependent colors, we use a Voxel grid storing local features, which is followed by a shallow MLP network. We reconstruct our scene representation in a coarse-to-fine manner, where we first reconstruct a coarse geometry. Then we use the reconstructed coarse model to find a tightened B-box and build an occupancy max, which can help us give a large number of queries in the fine stage. The fine stage model is finally optimized with a progressive grid scaling strategy. Finally, our method achieves NERF comparable quality, and our training time is many times faster than the stronger version of NERF. Please find out more results in our paper. There are some concurrent work using advanced data structure like org tree, hash table, and factorized grids. You will need them if you want to use a higher grid resolution. But I believe the simplest dense grid could still be your good starting point if you have other challenging problems to deal with. We have released our code with many improvements. First, we fuse some Python operation with CUDA and achieve another 2 to 3 times speed up. We now also support forward-facing and body 360 capturing and achieve NERF quality in about 15 minutes. We have also realized an efficient MIP-NERF 360 distortion loss. Our space-time complexity is linear to the number of points on a array, which is much efficient than the straightforward n-squared realization. The loss improves our training time and result quality, and our efficient realization could let more work benefit from the loss. Thanks for listening. Have a wonderful trip in CVPR.